Hello explorers and welcome to another video. Today I'm gonna continue with my devlog. So this is gonna be devlog 2 of the SQRL implementation. And the last time we talked about a little bit what the format is about and how the protocol works and what you can do with it. And today I'm going to go into more of the data structure when you save something to disk. And this is something that I need to figure out in order to read the secret key that was stored either on paper or in a file. And there's a lot to go through here, and there's a lot of different pieces in order to actually open up this format. So I'm going to talk about the different things in the format and also how to open it up and use it. So first off, if we look here, we have a signature at the top, SQRL data. It's 8 bytes and it's lowercase to indicate that this is a binary format. If it's uppercase, there is actually a case where you want to send this data over a line that can't handle binary, and in that case you can send it as an base64 URL encoded string, and then you will uppercase the header in order to signify that this will come as a different stream than binary. After that we have a length for the outer block of the first block. So in the first block in the series, there's 3 different blocks that we need to go through. The first access password block is 125 characters long in the outer layer. And then we have some type here, and then we have the plain text length, and that's the inner block of this little transition. So the inner block is actually the piece we see below here, including the header information at the top here. So that was something that threw me for a loop. So everything that is indented here is those 45 characters. So it has some IV, so that's an initialization vector for the IAS GCM. So that's a specific algorithm that uses AES to both encrypt data and verify its validity using a hashing algorithm that takes a counter that goes through and hashes all things. So it's quite an involved encryption standard that can be used to encrypt things and validate them. And then we have 3 values for the scrypt function, and scrypt is an encryption standard that will go through something, start from a random salt, and you add your password to that random salt, and then you iterate over a number of iterations in this case. So the scrypt don't have the actual iteration count. It just uses a lot of memory. So you will give it an n factor to tell it how large a memory space it will work through. So the scrypt is a function which creates a memory space and then jumps around in this memory space in order to find a value. And it's used in this manner just so that it's going to be hard for someone with integrated circuits and so on to actually repeat this process in a memory efficient and timely manner. So this is something that will take your password and create your unique key in order to unlock this block. And this will take some time, and that's where the iteration count comes in. So we have a value, we set how long time we want this password block or this data to be encrypted under. So how much time do we want the scrypt to spend in order to create my key from my password? And the iteration count is the saved value of how many times it had to run it in order to accomplish that time value. And then we have some option flags after that. We have a hint length for the number of characters. So if we want to have a smaller password and a simpler password for decrypting the data when in use frequently, then you use the number of shards in this hint value. And then you have the password verification seconds. So this is the number of seconds you will run the nscript function. So n stands for this iterating a lot of times over an script function. And how many seconds do we want this to run in order to create our password? So that's saved there. And then we have some idle timeout in minutes for wiping password. How long should the password stay in memory until we wipe it out of memory? And then after that we have the outer part of this block, and these are the master key. So this is something that is encrypted using AES GCM and verified by this verification tag. And the key for this function comes from the script. So you use the script with your password in order to create a key that you in turn use with AES GCM to verify and decrypt your password. So it's quite an involved format just to get your master key in order to make connections and talk to servers. The next block we have after that has a length of 73. So it stops by this verification tag here. We can make some spaces here. And this is the rescue code data block. And it also has an script function to actually take your rescue code. That's something that the application will create for you. And it takes that rescue code in ASCII and uses it as a password. So instead of using your password that you handmade, it will use this rescue code in ASCII to create a key for your unlock key. And if we looked up here, we had a lock key that we sent to the server in order to tell the server that this is our master key and it should not be able to we should be able to lock this down with this key. And this unlock key is used to actually create a new master key if or authenticate with the server again if we lost our master key or if there was some problem. Then we will use our unlock key to create a new identity and keep the connection to the server with this key. So this is a very much more secure block. This rescue code is quite large, and this will be saved and never, I repeat, never be saved on a device. It will only be saved to some keying material when you export your key. So this rescue code is created once, and then you have to print it out and keep it at hand on some remote place. And this identity can be saved somewhere, but the rescue code will always be separate. So in order to get this very secure key, in order to unlock your data, you need your rescue code, and that you should keep stored away somewhere. And the last block, block 3, that's previous identities. And that's if you want to rekey your identity and change identity. Let's say that you don't trust your identity anymore. There was some server that used your identity in some way that you didn't want to, and you wanted to create a new identity. Then this format also supports that. So here we have 3 old identities that we can keep over the internet, and as we go through and use the old keys, we will update our information on the internet with the new keying data. So these are just to keep our keys current as we go through them on the internet. And this is also very simple. It has some length and a type of 3, and then how many previous keys we have. So that's either 1, 2, 3 keys, and then we have the specific keys. Those are also 32 bytes, and a verification tag. And this keying information down here is also encrypted, but these are encrypted by our master key. So in order to update the previous keys, we need our current master key to unlock this encrypted piece here. So here we don't need the decrypt function. And as you see on the second block here, we have an SQRL function that isn't using an initialization vector for the unlock. So the GSM AES is used here as well, but the initialization vector is actually set to just zeros. So it doesn't have any initialization vector that is specific for this key. And that's because the master key can be saved again, saved multiple times on the same device, and then you want to change the initialization vector when you create it. But this rescue key will never change. It will be created once and saved for this identity, and then it will be stale. So then you don't need an initialization vector that you can update. So let's go through some more code here. Where should we start? We can start by looking into the let's see here, read function. We actually have a function that we read our data. So here we have a byte input, and then we copy the first 8 bytes from this input and check that the actual header is correct, or else we will throw an exception. And then we set the offset after the header, so we will start there. We read our first length, and then we have some header fix here in order to shift a bit where we want to read from inside of this loop. And then we read the length for the first block here, and we check how many what the length is for this block, and then we will check if that length is past the length of the full input, and if not, we will handle that block. So we will take the array, copy the range out, and so for this block we will separate the block and handle it separately, and then we will add the length to the offset and also the length to the reader offset to be after the actual length metrics. And then we start the process over to read the data again. So that's how we do the reading part of all the blocks. Down here I have a little experiment that I wanted to take the recovery code and also the previous keys and create a verification recovery block that I will show for the user in order to verify that they actually have read in the key correct, because the recovery block and all the previous keys will actually be saved in ASCII or base 56 on the sheet of paper. So I wanted to present this to the user when they are unencrypting their storage block, in order to create safety that I actually have read the key correctly. And then we have the handle password block. It's not that much. We just copy all the different lengths into their separate fields in the data. And I also have this handle identity block, and here again I read all the data from the paper into memory. And lastly, I will read the previous identity block, so I get all the information of the previous keys. And here you see that I handle it differently depending on how many keys I get. I will read them in and save them in the different key blocks. And I think I don't need the fourth key. I think there is only 3 keys, right? Well, so that's how I read the different blocks. And then we have this little handle block here, and this is very simple. I just read the length of the block and the type of the block in order to choose which of these function to run, either the handle password block, identity block, or the previous identity block. So there's nothing special there. I have 2 small functions here to read either 2 bytes or 4 bytes and return an integer, because I needed to read lengths and other information saved in bytes. So I wanted some simple functions to help me out to actually shift those correctly and get ints back. And then we have the decrypt identity key function that actually decrypts your identity in order to authenticate to a server. And it takes a password. And as I have built this application at the moment, I use functions that is only available in Oreo. So if I have an Android build that is older than Oreo, I will actually return false here. There is implementations in Sodium and so on that you can add to your application, but for ease of use, I wanted to have as small of external dependencies as possible in order to make the implementation phase a lot faster. And as the AES GCM is built into Android Oreo, I wanted to start there. And then I have my little progress updater here. It's just something to show a progress bar when I actually use the application. So we don't look at that at the moment. That's more into the implementation of the GUI. And then I have my little library here for encryption utils, and I have my SQRL here. So this takes a lot of different things. It takes the password, some random salt, the nlog factor we talked about earlier, the key length 32, the iteration count, and then progress updater. And if we go into SQRL here, it will use the SQRL from a library I found on the internet. That takes the password, random salt, and the log n factor is actually how many times you should shift a 1 in order to get a size. So in this case, I think they have a 1 shifted 8 times. And then we have 256, which is a value that is chosen by GRC that has the protocol. So that's just used here. And then we have the length of the key, which also is chosen to 32. So I could have hard-coded it here as well, but I sent it in just for ease. Maybe I should send in the R value as well, but I don't think that R says so much. So maybe I will look into what this actually says. This P value is important because that is how many processes to run this SQRL function under, so you can run it faster by using more kernels, but you want to run it slow, so we set it to 1 kernel in order to not have it as speedy as possible, because we want the time actually. And then we have this progression timer here that we take a start and end time, and that is just to know how much time one SQRL takes. And that is something that I will use then in my progress bar, so I can estimate how much time it actually will take to do all of them. And then I will XOR my key with I will copy my key into the XOR key, and this XOR key I will actually XOR with each iteration of run with this password. So I copy the first password result over here, I rekey again with the password and the key as my salt, and then I XOR the result in order to get a new key for the next iteration, and so on. So we always get an XORed value from each key run, and that's the actual value that is the result of this NS encrypt. So that's how we create the key that will actually open up our little vault. Then I use things that are built into Android, so I use secret key spec, AES with my key. I create a cipher for AES GCM no padding, and then I set some GCM parameters and add my initialization vector to that. I want a 256 length of the result, verification code, and then I start my decryption. So I set decryption mode, I add my key spec and my params. So now I say that with this key I want to decrypt it, and I want to verify within the verification tag that has this initialization vector. And then I add my plain text as an additional data. So this is some data that is not encrypted, it's just plain data that is verified. So that's the first 45 characters that we talked about earlier. So those are open but verified that they are actually correct. So this tag will verify the validity of that plain text. And then I add my two keys, the master key encrypted and the lock key encrypted. And I do a cipher final with the last bytes, which is the verification tag. And when this runs, it will check the last 128 bits that they are equal to the sent in value at the last point here. So the verification tag must actually match the last 128 characters, and if not, it will throw an exception and say that this was not a valid decryption. And when I have decrypted, I get some decryption result, and in that result we have both the master key, which is the first 32 bytes, and then I get another 32 bytes, which is the identity lock key decrypted. So I actually have a little bit of a typo here, I see. It should not be identity lock key encrypted, it should be identity lock key, because the encrypted value we got up here, and then we get the unencrypted value down here. So we have both, and if everything goes right, we return true. So that's how we decrypt the key. And then I have a function to actually decrypt the unlock key, which uses the rescue code. As you see by the gray here, I don't use it at the moment. It's not built in my client, but I have it, so I can do that later. I also added a little function here that I use in my communication later, where I needed an HMAC as a private key for my communication. So that will take my identity key, the unencrypted private key, and create a private key for a specific domain. So every domain gets their own private key that I will create a public key for later. So this is the little function to get a private key keyed for a specific domain. Also a very small function. So this is my little storage API that I built to read in the GRC or SQRL storage data and use them in my client. In this, I have all the way I have just decrypted data. I've just stored them in memory. I have no function to actually clear the memory. I have no function to save data and so on. And that's things that I need to add later. But in my first simple implementation of this protocol, I wanted to decrypt the data, do a successful login and account creation, so you can actually build a tool that you can use if you have a key and you have somewhere you want to log in. I hope that you found this little tour through my storage reader interesting. If you have any question about this format or about SQRL in general, please leave me a comment down below. I hope that you like my format and that I do these little devlogs, what I'm working on at the moment. And if you haven't subscribed yet, please do that, and I really hope to see you in the next video.